The initial step in our analysis involved utilizing FTIR, which stands for Fourier Transform Infrared Spectroscopy. This technique allows us to examine the molecular compositions of a substance by studying its interactions with infrared light. By assessing the provided spectrum, we observe two distinct peaks. To interpret the spectra, we first refer to a table that guide us through the relevant regions. The initial peak appear at a wavelength of 2994 cm-1, displaying a strong intensity and corresponding to CH strength G. The second peak emerged at 1330 cm-1, also exhibiting a strong intensity, indicative of Cn strength G. Based on our observations, we determined that the molecular structure corresponds to 1-ethyl piperidine. This particular structure is classified as tertiary amine due to the presence of central nitrogen atom surrounded by 3 attached alkyl group. As a result, the compound does not exhibit the NH stretching vibration commonly found in primary and secondary amine. Finally, the functional group identified in this compound is an amine.
So we move to HNMR spectroscopy. We can see from the given table that show 4 significant peaks, meaning there are 4 different H environments. We can confirm from our compound that it has CH3 molecules and HT will represent it. The tallest peak indicates the abundance of hydrogen atom or proton. Applying the n+1 rules, we can find the multiplicity of the neighboring H atom, which is a triplet. Hc is located between the CH3 molecules and the N atom. Applying the n+1 rules, we can find the number of multiplicity of the neighboring H atom, which is a quartet. Again, HA is located in the cyclic between the N atom and the CH2 molecules. Due to the fact that CH2 is bonded with the strong EDG and R2, the peak will be located at the left of the spectrum. Applying the N1 plus rule, +1 rules, we can find the multiplicity of the neighboring H atom to neighboring H atom +1, which is a triple. All the carbon on the CH2 is considered as the same environment. You can see on the slide. Applying the n+1 rules, we can find the multiplicity of the neighboring H atom for neighboring H atom +1, which is a quantet. Equal to 5, which is a quantet. Thank you very much.
So basically, how to determine the structure of compound by using the CNMR is firstly, we can divide up the region of the carbon-13. So as we know, the range of the carbonyl compound is between 116 until 220 ppm. Meanwhile, for the sp2 hybridase is from 110 until 220 ppm. But what we can see for both regions in the spectrum are empty. So we can assume that the compound will not have any carbonyl, aromatic or alkene structure. But what we can see, the signal is in between the range of sp3 hybridase carbon, which is shifted to the upfield area. Next, from the spectrum, there are 5 signals, which mean there are 5 different environments of carbon in the compound. So, if we look at the compound structure of 1-ethyl piperidine, there are 5 carbon that contain different environment. The carbon is labeled as carbon 1, carbon 2, carbon 3, carbon 4, and also carbon 5. So, to determine which carbons are assigned for every chemical shift value, we must look the atom which is attached to them. For example, carbon 1 and carbon 2 both are attached to nitrogen, so we can see the chemical shift is between 10 until 65 ppm. For carbon 1 is adjacent to the secondary carbon and carbon 2 is adjacent to the primary carbon. So between carbon 1 and carbon 2, carbon 1 will have the higher chemical shift compared to the carbon 2, even they have the same functional group. Therefore, carbon 1 will be the one at 54.27 ppm and carbon 2 is going to have the signal at 53.09 ppm. Basically, they are shifted slightly downfield compared to the alkane carbons due to the electron withdrawing effect of nitrogen again causing the deshielding. Next, for the other three last signals, they will be the carbon which attach to the primary, secondary or tertiary carbon, which is alkane, as they are ranged between 10 until 35 ppm. For carbon 3 and carbon 4, both are attached to the secondary carbon, but for carbon 3, it attached to the secondary carbon which is closer to the nitrogen atom. So that's why carbon 3 value of chemical shift is 26.12 ppm, which is higher compared to the carbon 4, which is 24.66 ppm. Lastly, for the carbon 5, the value is 12.10 ppm, which is shifted to the upfield region and has a lower chemical shift value because it is more saturated.
Okay, next we move to mass spectroscopy on how to determine the molecule compound when the mass spectra is given. Okay, the first step is we need to identify the molecular ion. The molecular ion is typically represented on the mass spectrum as the peak with the highest M over Z ratio. As from mass spectra given, there is a peak seen at M over Z 113, and this peak represents the molecular ion. The second step is we need to identify the major peak. A major peak is the most abundant peak within a cluster of smaller peaks. Base peak is equivalent to peak with the highest intensity. From our mass spectra, the major peak is at molecular ion itself, which is M over Z 113, followed by 98 and 42. M over Z 98, also known as a base peak because it has highest intensity. And the next step is we need to determine the mass difference. Step 2 is used to determine the mass difference between each peak and the next peak on the spectrum. As from the mass spectra, the mass difference between major peaks starting from the left is 56 and 15. And step 4, we need to identify any heteroatoms. If there is M plus 2 peak, this indicates the presence of halogen. Larger different mass show the presence of heteroatoms. From our spectra, there is no M plus 2 peak, so there is no halogen in this compound. The larger mass difference occur because the compound lost cyclic compound due to fragmentation, while the 15 mass difference indicates the presence of an nitrogen atom. Okay, last step is we need to naming the molecule. Combine the name from the number of carbon with the heteroatom to give the chemical compound. As from the spectra given, with 113 molecular ion and the presence of nitrogen, we assume that our compound is 1-ethyl p-pyridine.